So this YouTube is about projectile motion, and what we will assume here, as does the book, is that there is no air resistance. So the scenario is a mass is launched at some velocity v0, and so that means it's launched at some speed with some direction theta with respect to the ground. The mass then goes into the air, it gets to an apex position, then it comes back down again and hits the ground, as we all know. So this motion is the motion of a thrown ball, it's the motion of a kicked soccer ball, it's the motion of a cannonball, and we're idealizing it by ignoring air resistance. So the simplifying feature here is that if you look at this mass m, whatever it is, be it ball or cannonball, only has a vertical force acting on it. It only has the vertical force of gravity acting on it, its own weight, in other words. And so by Newton number 2, that means that there is no force in the x direction, and therefore there's no acceleration in the x direction, and therefore the velocity in the x direction the whole time as it's in the air is constant, and therefore its velocity the whole time it's in the air is equal to its initial x velocity, but its initial x velocity is simply the x component of its total velocity. Remember, velocity is a vector just like force, and so we are in this picture, we're decomposing v0 into an x component, v0 cosine theta, pointing to the right, and a y component, v0 sine theta, pointing up. And so Vx is equal to v0 cosine theta the whole time the ball is in the air. No change in the x velocity. In contrast to that, in the y direction, there is an acceleration of minus g by Newton number 2. Therefore, the y velocity as a function of time is equal to the initial y velocity, which you can see right here, minus g times t, using the appropriate kinematic equation. So the y velocity is not constant. So to give you two illustrations of projectile motion, let's consider, first of all, a ball launched horizontally off a table surface that is 1 meter from the ground. And so h is equal to 1 meter. We're going to embed coordinate systems in here. So the coordinate systems are as shown in the blue axes here. Furthermore, let's say that we know the ball launched horizontally off the surface of the desk lands 3 meters from the base of the desk when it hits the ground. So we'd like to be able to see if we can use projectile motion to compute what this horizontal launch velocity is. Turns out to be very easy to do. If we use the y equation in the g direction, y0 is equal to h, which is equal to y of 0 is equal to h, which is equal to y0. Vy0 is 0 meters per second. Look back at this diagram and understand that this is true because the launch velocity is purely horizontal in this example. And so you can use a y equation in the y direction and state that y equals y0 plus vy0 t plus 1/2 ay gt 1/2 ay times t squared. This term drops out because vy0 is 0. And so essentially, if you want to find the time corresponding to when the ball hits the ground, you set y equal to 0. Look at my coordinate system here. When y is equal to 0, the ball has hit the ground. 0 is equal to h minus 1/2 gt squared, substituting minus g in for a sub y. This equation can then be solved for t. T is equal to 2h over g square root. So that would be, if you assume 1 meter for h, the numerator inside the square root is 2 meters. Should be meters inside there. Divided by 10 meters per second, using easy numbers for g. That turns out to be the square root of 0.2, which is 0.45 seconds. Please note the air time is independent of V naught. So V naught can be anything. As long as it's horizontal, it's going to take this mass the same time to fall this distance. Okay, make sure you understand that. Now, with this air time in hand, I can go back and I can relate delta x to the air time to Vx naught. That's which is what I'm trying to find here. So Vx naught simply is equal to delta x over t. Now this is true again because the horizontal velocity is constant during all of projectile motion. So delta x is 3 meters by assumption, and the air time is 0.45 seconds. And so if one divides 0.45 seconds into 3 meters, one deduces that the initial horizontal launch velocity is 21.6.7 meters per second. Second example, let's get a theoretical expression for the range of projectile motion launched from the ground and returning to the ground. I'm going to use the same coordinate systems as I did last time, and same geometry with Vy naught at some angle theta with respect to the ground. And so the first thing I'm going to do is I'm going to compute air time. So air time, I can use the velocity formula, which I believe is at the top of your kinematics formulas. When the mass returns back to the ground, just before it hits the ground, it's going to have the negative of its initial upward y velocity. And so the velocity just before it hits the ground is going to be minus v naught sine theta. This is the initial velocity minus g times t is going to give me an expression that I can solve for t, and this is going to be the air time. And so solving this equation for t, I get t is equal to 2v naught sine theta over g. So check the units real quickly. On the numerator, we get meters per second. In the denominator, we have meters per second squared, which gives me the dimensions of time. So that's how long it's in the air. So you can see, for example, for a given v naught, I can affect the air time in the air by changing theta. If I keep theta the same, I can increase the time in the air by increasing v naught. Let's calculate the apex height. That would be the height, the highest height from the ground that it achieves. And so the way I can do that is I can understand that the average velocity between when it leaves the ground and gets to the apex is its starting y velocity plus its ending y velocity, which is 0 when it's at the apex. So starting plus ending divided by 2 times the air time to the apex. Well, the air time in the apex is half the time its full air time. In other words, there's equal time for the mass to get from here to here as there is for it to get from here to the ground. So I can take this and divide it by 2, which is what I've done. So the average velocity times the time taken, I'm using the last equation on your card now, is going to be this. And so I get a 2g downstairs, and upstairs I get a v naught squared sine squared theta. Finally, the range, delta x, is simply equal to the constant x velocity, which is v naught cosine theta, it's just the x component of the initial velocity, times the air time, which we computed in this first go here. And so that just doing some simple algebra, is 2v naught squared cosine theta sine theta over g. Now there is an equation from trig that you may or may not know, so I'll just tell you. 2 cosine theta sine theta is equal to sine 2 theta. And so this expression simplifies to v naught squared sine 2 theta over g. Either one can be used to predict what the range of a projectile is. And interestingly enough, it goes as velocity squared. So if you keep the angle the same, projection angle is kept the same, and you double the velocity, your range will increase by a factor of 4. If you triple your velocity, your range will increase by a factor of 9. Something we wouldn't have known without doing a theoretical analysis like this.